So this will be about machine learning again. It will be in particular a bit about distributed machine learning if the data becomes too big to fit onto one computer. And yeah, let's get started. Before I'm doing some shameless advertising for the meetup groups there are. So we have this Computer Spark meetup, which is brand new. Then we have this other meetup, which is a bit older. If some more of you join today, we might reach 1,000 members today. That would be nice. So join us in 2 months. So machine learning and artificial intelligence. Everybody is talking about this at the moment, and so yeah, people think it's very useful, of course, to solve the very important problems for humanity in this century. Mostly, for example, classifying pictures of dogs and cats. So that's what we're trying to do here. So we have many pictures, and from this given picture, we want to say, is it a dog on it or is it a cat? So that's classification, and actually we have already seen the entire pipeline, how this works very nicely in Mark's Journey's talk, classifying if a customer is going to jump away or not. And here is the same kind of question, it's just a yes-no question, this or the other animal. So we have a training data set, which is the most important thing. So for the training data, we assume that we know what the truth is. So we know that this is a blue point when it's a dog. We know it's a red point if it's a cat. And yeah, what is the point actually? So that's just a big list of numbers, of course. And what these numbers are just the pixel values. So just fill in all your data into this long list, and that's the vector, that's our features. That's what for us is a data point. So, and for this, we have this additional label information. So we want to classify these guys, and we want to be simple in the model we choose. We choose a linear model to do this. So we just use a line to separate these two, or a plane if you want. This is maybe not the best plane to do that. So here is a better plane trying to separate this. This one is actually nice because it's perfectly separated. So this is what we call training, the defining of this plane. So that's all good and nice, but now actually, so we have already seen how do you use that and how do you then evaluate it and stuff. So here comes a new picture of something you don't know the answer. So that's a test point, not a training point. And what's the answer going to be? It will just be on which side of the plane is it lying. So this is rather on the right side. So the system is going to answer it's a dog. So that's how this works. We want to look a bit into the algorithms to do this. And essentially this is all trained by the same type of algorithms. And they are actually really simple in the way that they just look at one data point at a time and do some update to your model. So this is the model, the plane. It's described by its normal vector, the vector orthogonal to the plane. So we want to find the best weight vector for this. So this is, as we said, a bad kind of choice. So we want to improve it. And how are we going to do this? We're going to find one of these points, and we are going to look for one which is wrongly classified at the moment. So this guy is wrong. It should be on the upper side of the plane, but it's on the other side. So this misclassified point, we're going to use it, and actually we're going to add it to our weights vector. That's everything the algorithm does. So we're going to add a little bit of this wrong classified vector, and that's our step. Now you can see the plane has turned a little bit, and it's already a much better classification plane than we had. This algorithm is nice because it uses one vector operation in every iteration. You just need to add these together. And it only looks at one data point per iteration, so the cost is very cheap. And that's actually the algorithm that like 90% of all machine learning applications are trained to this algorithm, including the deep learning algorithms at the moment. So This is not so new, this algorithm has been known in the 60s for just finding some plane which is separating. Now they're more looking for the plane which is best separating. And also now we understand better how this model still works when the points have noise in them. If some of them are completely wrong, then the same algorithm still works. So yeah, what has actually changed? And as this has been mentioned many times, of course, this is the New York Times in the 60s. They were already very enthusiastic about this kind of methods. About the same thing that we have seen, that we're saying, yeah, this is like the beginning of a small system that tries to learn, it tries to understand, to talk, whatever, understand if it's a cat or a dog. I don't know what the application was back then. So this is the New York Times 3 years ago when, yeah, so everybody still agrees that the most important task is cats and dogs, so Google has thrown 10,000 of computers to these tasks to, again, do the same thing using a very similar algorithm we have described, basically the same. But today we just have so much more data, which just makes it yeah, much nicer, gives us so much more nice applications, and also the computers have become a lot faster, like 1,000 billion times faster. So, yeah. Okay, machine learning, there's some more applications. We have seen many, like the same thing for cats and dogs is used to classify is this type of galaxy or another type, or is it an exoplanet which has passed by or not, if you have several pictures at the same time, different times. Yes, medical images, that is in Kevin's talk, are very important, and lots of data is being collected. Recognition of handwriting, self-driving cars, they need to do a lot of classification and regression. They have a regression task to do to say, are they in the middle of the street? They have a classification task to do, is this thing beside the street, is this the stop sign, or is it somebody walking into the street? So there's a lot of classification and regression going on in all these applications. And yeah, another really cool application was the one we've seen in the morning, like estimating the age of a person and the gender. I had some fun with Fico Jacobo this morning on all these characters. Just play around with this website. Text data, we are also very interested in sentiment classification, as was mentioned in Kurt's talk. This is tweets. This text data is very high dimensional, so you have many, many entries in these vectors. So you want to look for sparse solutions, maybe. Medical data and Watson. So medical data, like genes, is of course almost like a text. So we use the same method for text classification then for genes. And yeah, you know all these applications. Audio and sensor data is where you collect more and more. And this nice application where you draw on your touch screen, then you will recognize if this is this word you meant, or if you meant some other word on your phone. Again, this is a classification task. Have you meant this word, or were you trying to draw another kind of word? Sorry for that. Okay. Just about applications. The other one is recommender systems, and then recommender systems are again trying to do regression to say how many stars would you give to this movie. You haven't seen it, but you have seen similar movies which you liked or did not like, and also it's kind of a classification task. Would you like this product or not, and all kinds of similar applications, and more data being available, making this more and more interesting to find patterns in the data using exactly these techniques that we have described. So I really encourage you to play around with machine learning tools. And to get started, so I really recommend you to go to kaggle.com, because there's so many competitions going on there, and this is also nice if you're planning a business case which one is trying to use machine learning, because then you can really get a feeling for what is actually possible, what are people like achieving on this kind of data. Because like many commercial vendors just sell things out of the blue that this is perfectly possible or not, but in such a competition setup you really see what people are doing and what is actually possible to find out of this kind of data, and furthermore it's really fun to play around with this. And then scikit-learn is a really good package, which is well documented if you want to start playing with data, if you want to use machine learning algorithms so you don't have to implement them yourself. Yes, this was machine learning on like one computer, but now what if the data does not fit onto one computer anymore? If you need maybe two computers. So here again our data points. I visualize them as columns, and so far everything was good. I had my nice algorithm for solving my task, but now my data became too large. I will have two machines which I have to use. This is a big problem because all the items will kind of break down. They work very nicely on one computer, but not on two anymore. So before we're talking about the distributed algorithm, it's very important to also ask, like, do you even benefit from more data? And this, I think, is even the more fundamental question, that you should really be sure that how much you actually gain from the amount of data you have, or for your task, is it actually enough to just throw away the additional data, or do you really have additional value when you use all the data? So just saying, like, both can happen, and it's important to try out and to work with, to study this trade-off, like how much data is it worth going to use. So like in my research, we are really interested in this case when you actually have to use more than one computer. So let's see what we can do there. So we have already seen the algorithm on one computer, so why not just use the same algorithm on these 5 computers and then talking together to solve the problem. So the problem is to find a linear classifier on all these data, like the best separation. So what we do now is every machine will work on its own data. It will select one point which is wrongly classified. It will compute an update. So delta of the weights, that's like how it suggests to update the weights. And so all these 5 updates we have then computed, we're going to send them to the others, so that now we have the shared vector again, so now everybody's talking about the same classifier again. So that's all nice, and that's actually done sometimes. So there is a problem with this approach, that it needs a lot of communication. Because the steps are so cheap. Like the steps is just looking at one vector. Once you've done that, you have to communicate. So the communication is usually much slower than the whole computation you do. So how much does it cost to just look at the vector? So this is in RAM, we assume, so maybe it has 100 entries. Then it takes about 100 nanoseconds. And that's also the time it will take us to do a step on a computer, because we just add it up. Okay, then we send it to another machine, and it's easily 5,000 times slower, because it has to go through an Ethernet cable, I don't know, some communication has to be set up. Or if you do Hadoop, then it's even much worse, because then the communication round takes several seconds, which it can certainly not afford compared to like 100 nanoseconds to just do one of these steps. So we need to be much more efficient with communication. And yeah, depending on the framework you use, of course this is different, but I'm just saying this is a huge contrast that you should keep in mind when designing these algorithms. Okay, There is a second problem, kind of, that it's kind of really annoying to do parallel programming. This is a pain. Like, it's so annoying that, yeah, basically everything is annoying. So you have to wait, you have to see that nothing goes wrong, that these threads talk to each other. I don't even know how that really works. So we want to use a simpler framework, like MapReduce is simple. There you just write one line or so, and this says this operation is going to be applied, and then the result is going to be communicated. That's fine for us, but we don't want to do programming on a supercomputer where you have to see code and MPI this. And furthermore, the annoying thing is that people have already done really good algorithms on a single computer. But now that you have 2 or more machines, this breaks down, you cannot use them anymore. So we would like to have a framework where people can reuse the algorithms on the single computers. And that's the goal of our approach. Before I get there, I have to say that it's not enough to just let every computer do the problem on their own data and then take the average at the end. This has nothing to do with the true solution. So this is just to say that this machine learning problem in classification and regression, they're not so hard, but also they are not as easy as that you could just then take the average of everybody doing part of the work. If here everybody would do just 2 data points on these 5 computers, then the average would be somewhere here, but the true best classifier is the one from here, and these machines don't know. So it's just to say that you need to communicate more, but you want to still avoid communication as much as possible. Okay, so then we come to the framework we're working on at the moment. This is what we propose. This goes a bit more technical. I cannot discuss all details, but it uses, the idea is to kind of compress the state of the other computers such that you know what they already have done. Such that so like you're on this machine number 2, you do some work, but you don't want to screw up what the others have already done. So you need to kind of know like if they're already optimized their entire data or not, and you need to take this into account. And the way we take this into account is by using this shared classifier vector for this information. And we have formulated a different optimization problem, which you can do when you only have your local data, but which respects that you're not going to screw up the work of the others. That's a high-level idea, and for more details I have to forward you to the paper. This is all online. And again, you not only do this once, but you do this many times. The good thing here is you just use your local solver of your choice. You use the algorithm which already worked well on one computer. You can just plug this into our framework, and this is going to work. Also, you're going to run it for how long in each round? You will just run it as long as the communication will take time. So that then on your cluster, it will have the nice property of saturating both the communication and the computation. I mean, every cluster is completely different, and we really don't want to deal with that. So we want to automatically have the algorithm doing as much communication such that this matches how slow your communication is. And this we can do by just choosing how many steps you want to do here. Okay, that's all. We apply this to classification and regression. These are the linear classifiers we've seen. We have some generalization to structure prediction, which is something that predicts something more complicated than a yes-no answer, like a multi-class or a sequence as an output. Then we have regression. There it's both. It's a bit different if you have a sparse regularizer or not. But in any case, we do least squares regression. And we can deal with different regularizers you want to use, like the lasso or ridge regression or elastic net, whatever you want. And yeah, don't bother too much about the formula. That's all. We implement this on Spark, and we compare to the MLE package, which essentially uses the algorithm we described at the beginning, this stochastic gradient descent. So on the vertical you have the error, and on the horizontal axis we have the time. And so we are the red line, and the MLE implementation is roughly around the blue lines, so you can see that this is quite an advantage on a commodity cluster, on a cloud system. This is training a support vector machine on some data sets which are, it doesn't even matter if you have more features or points, it works in both regimes, it works relatively nice. I mean, this is not tied to Spark, but of course it nicely fits to be implemented in Spark, because there, writing this communication is really just one line. You write that this vector is going to be summed up, and our code is open source on GitHub. Please look up and give us some feedback. We'd be happy about that. We're also working on integrating this into MLE potentially, and yeah, thanks for your attention.
Thank you, very interesting. So another Spark library that comes out soon, hopefully, that we can use. Questions?
So you mentioned having the saturation of both sort of I/O and processing time by running it as long as necessary. But I assume the time you allow it to run on a single node affects the conversions.
Yes.
So if you run it for a really long time on a single node, then it takes longer, I assume, or more iterations to convert.
Yes, you're right. This is a trade-off. You could run it very long on a single machine and do almost no communication at all. But then you can see that it becomes a bit worse. So this is exactly this trade-off. You will communicate as much as you can, but like not more than your system allows. That's maybe the bit vague answer to that. But we also have some conversions theorem where something like this kind of appears, but then in practice you can also see this in the experience.
This Cocoa library, is it running within the Spark biosphere, or is it outside of it?
We just put it on Spark packages, so it's really, it almost looks like the same as the algorithms which are in MLE. So this is not, it doesn't take more than 100 lines to implement.
Okay.
So it's not so bad. And yeah, look up the GitHub repository, the two of them actually.
I also have a question, because Spark also does say they're doing parallel machine learning. So did you also try to implement the same thing and compare it? Because I suppose you implemented another algorithm that we don't have in there yet.
So the blue line here is basically what Spark has in MLE. Yeah. And now, like just today, there was a new version released where they have a better algorithm, which is second order methods, and we have not compared to that yet, but we hope we are still a bit better, but we're not entirely sure.
Sorry, beats Berkeley, I like this. Good. So